History of Jupiter, the Colossus of our solar system. Let's continue our documentary series dedicated to the planets of the solar system, with the goal of comprehensively describing their history and characteristics. After exploring the scorching plains of Venus, the red deserts of Mars, and the torrid little world of Mercury, it's time to leave the inner rocky planets behind and turn our gaze toward the first of the giants, Jupiter, the Colossus of our solar system, so massive that its gravity influences the entire planetary equilibrium. In this new chapter, we won't limit ourselves to describing the best-known features of this imposing planet. Instead, we'll go beyond, exploring its complex atmospheric structure with the iconic Great Red Spot, its extremely powerful magnetic field, its fascinating ring system, and the surprising entourage of moons that accompany it, some of which might harbor subsurface oceans. Comprehensive means exactly this: a detailed account rich with information and insights that will lead you to look at Jupiter with new eyes, appreciating its complexity and hidden charm. Jupiter is a planet of contrasts and decidedly surprising characteristics. The fifth world of our solar system, so massive that it alone contains more than twice the mass of all other planets combined, so large that it could contain over 1,300 Earths within its volume, yet so rapid in its rotation that it completes a turn on its axis in less than 10 hours. So imposing that it creates a magnetic field 14 times stronger than Earth's, but lacking a solid surface to walk on. Its atmosphere, a whirlwind of colored bands and cyclopean storms, hides a world whose composition mirrors the primordial nebula from which the entire solar system was born, a living archive of cosmic origins just waiting to be deciphered. But let's proceed in order and get to know this planet better through its numbers. With an equatorial diameter of 142,984 kilometers, or 88,846 miles, about 11.2 times that of Earth, Jupiter is the largest planet in the solar system. Its mass is approximately 318 times that of Earth, representing 71% of the total planetary mass in the solar system. Despite its imposing dimensions, its density is surprisingly low, 1.33 grams per cubic centimeter, 82.9 pounds per cubic foot, less than a quarter of Earth's, as it is composed primarily of light elements like hydrogen and helium. Jupiter orbits the Sun at an average distance of 778 million kilometers, or 484 million miles, or 5.2 astronomical units, completing a revolution in 11.86 Earth years. Its orbit is relatively a little eccentric, with a value of 0.048, causing its distance from the Sun to vary less than many other planets. The gas giant rotates on its axis in just 9 hours and 56 minutes at the equator. The deep internal rotation is slightly different, about 9 hours and 50 minutes, making it the planet with the fastest rotation in the solar system. This rapid rotation causes a notable polar flattening, with a polar diameter almost 9,300 kilometers, or 5,780 miles, less than the equatorial one. The axial tilt is minimal, only 3.13 degrees, which means Jupiter doesn't experience significant seasons. The temperature in the upper part of the clouds is about minus 145 degrees Celsius, or minus 230 degrees Fahrenheit, while pressure and heat increase dramatically going deeper. The surface gravity, measured at the level of visible clouds, is 2.4 times that of Earth. If you weigh 70 kilograms or 154 pounds on Earth, you would weigh 168 kilograms or 370 pounds on Jupiter. This cold, objective data doesn't tell the true story of this gas giant, however. Its biography is written in the complex patterns of its cloud bands and in its vortices that last for centuries. Lacking a solid surface and with an atmosphere that gradually fades towards a perhaps rocky core, Jupiter represents a type of world completely different from the inner rocky planets. Its clouds, organized in belts and zones of different colors that surround the planet parallel to the equator, are the visible result of powerful jet streams flowing in opposite directions at different latitudes, creating turbulent boundaries where vortices and storms form. The detailed study of Jupiter became possible only after the invention of the telescope, although the planet was known since antiquity as one of the wandering planets visible to the naked eye. Galileo Galilei in 1610 was the first to observe it with a telescope, discovering the four major Jovian moons, Io, Europa, Ganymede, and Callisto, now known as the Galilean moons. This discovery was revolutionary, providing one of the first observational proofs that not all celestial bodies orbited around Earth, thus supporting Copernicus's heliocentric model. Since then, Jupiter has continued to fascinate astronomers of every era. The Great Red Spot, perhaps Jupiter's most iconic feature, was first reliably observed by Italian astronomer Giovanni Cassini in 1665. It's an immense anticyclonic storm, large enough to contain 2 or 3 planets the size of Earth, that has been raging for at least 350 years, although in recent decades it has gradually reduced in size. Its reddish coloration is probably due to chemical compounds that are brought to the surface by upward currents and then altered by solar radiation. Jupiter's visible appearance is dominated by the alternation of light and dark bands running parallel to the equator. The light bands, called zones, are regions where gas rises upward in the atmosphere. The dark bands, called belts, are areas where the gas descends. This zonal aspect is the result of the planet's rapid rotation combined with the convective motions of the atmosphere and the Coriolis effect, which bends the ascending and descending currents in opposite directions in different latitude bands. Jupiter's atmospheric composition largely reflects that of the primordial solar nebula, being composed of approximately 89 to 90% molecular hydrogen and 10% helium, with traces of methane, ammonia, hydrogen sulfide, and water vapor. The visible colorations in the clouds are due to the photochemical compounds produced by the interaction between sunlight and these trace elements. In particular, sulfur and phosphorus compounds are responsible for the brownish and reddish tones, while crystallized ammonia forms the higher white clouds. Jupiter's internal structure still presents many mysteries, but current models suggest a layered organization. Below the visible cloud layer, the atmosphere becomes progressively denser until it transforms into an ocean of liquid hydrogen. About 10,000 kilometers below the clouds, the pressure is so high that hydrogen assumes a metallic liquid state, in which electrons are free to move, making hydrogen an electrical conductor like metals. This layer of metallic hydrogen in rapid rotation is believed to be responsible for Jupiter's extremely powerful magnetic field. At the center, probably there is a solid core composed of heavier elements, with an estimated mass between 7 and 25 times that of Earth. This magnetic field is the most powerful among all the planets in the solar system, about 14 times more intense than Earth's, and with a volume 20,000 times greater. Jupiter's magnetosphere is so vast that if it were visible from Earth, it would appear in the night sky as large as the full moon, despite the enormously greater distance. This gigantic magnetic bubble traps charged particles, creating intense radiation belts similar to Earth's Van Allen belts, but much more powerful. The radiation is so intense that it represents a serious danger for space probes approaching the planet, requiring special shielding to protect the onboard electronics. Another notable aspect is Jupiter's ring system, much less showy than Saturn's, but no less interesting. Discovered only in 1979 by the Voyager 1 probe, this system consists of 4 main components: the innermost and diffuse halo ring, the brighter main ring, and the 2 outer rings called gossamer, veil, associated with the moons Amalthea and Thebe. Unlike Saturn's rings, which are primarily composed of ice particles, Jupiter's are formed by tiny dust particles, probably material ejected from the small inner moons due to meteorite impacts. The close-up exploration of Jupiter has been a complex undertaking, given the enormous distance from Earth and the hostile environment surrounding the planet. The first probe to visit the gas giant was Pioneer 10 in 1973, followed by Pioneer 11 in 1974. These missions provided the first close-up images and direct measurements of the Jovian environment, also discovering the existence of radiation belts and rings. The Voyager 1 and 2 probes, launched in 1977, visited Jupiter in 1979 and shortly after, providing detailed images of the clouds and discovering volcanic activity on Io, the first observation of active volcanism outside of Earth. A qualitative leap in Jupiter's exploration came with the Galileo mission, launched in 1989, which reached Jupiter in December of 1995 and became the first spacecraft to orbit the planet. Before entering orbit, Galileo released an atmospheric probe that penetrated directly into the planet's atmosphere, transmitting data for almost an hour before being destroyed by pressure and heat. The mother probe continued to orbit Jupiter for almost 8 years, completing 35 orbits around the planet and conducting in-depth studies of the Galilean moons, including the detection of a probable ocean under Europa's icy surface. The mission deliberately concluded in September of 2003 when the probe was made to plunge into Jupiter's atmosphere to avoid possible contamination of potentially habitable moons in case of malfunction. Other probes that have provided data on Jupiter during close flybys include Cassini-Huygens in 2000, headed towards Saturn, and New Horizons in 2007, headed towards Pluto. Both took advantage of Jupiter's gravitational assist to accelerate towards their final destinations, simultaneously collecting data and images of the gas giant. The most recent and technologically advanced mission is Juno, launched by NASA in 2011 and arriving in orbit around Jupiter in July of 2016. Specifically designed to study the composition, gravitational field, and magnetic field of the planet, Juno orbits on a highly elliptical polar trajectory that brings it to just 4,200 kilometers or 2,610 miles above the polar clouds every 43 days. This particular orbit allows the probe to avoid the zones of maximum radiation and to obtain a complete mapping of the gravitational structure, offering precious clues about the distribution of mass inside the planet. Its instruments, protected by a robust titanium case, include a magnetometer, a microwave spectrometer to study the deep atmospheric composition, an infrared spectrometer to analyze the upper atmosphere, and a visible light camera called JunoCam that has provided spectacular images of Jovian clouds seen from perspectives never observed before. The Juno mission required extraordinary engineering to face Jupiter's hostile environment. To withstand the intense radiation belts, the spacecraft's electronics are enclosed in a titanium vault, weighing 200 kilograms or 440 pounds, which provides shielding equivalent to that of a 9mm thick lead wall. The probe's solar panels are the largest ever used for a planetary mission, with a total surface area of 60 square meters or 645 square feet, necessary to capture the weak sunlight at that distance from the sun. Despite these precautions, NASA engineers had predicted that Jovian radiation would gradually degrade Juno's instruments, which is why the mission was initially planned to last only 20 months. Surprisingly, the probe has resisted much better than expected, allowing multiple mission extensions. The images sent by Juno show Jupiter's poles as we have never seen them before. A chaotic assembly of octagonal cyclones at the North Pole and pentagonal ones at the South Pole, which remain stable over time, defying our knowledge of fluid dynamics. The probe has also revealed that the atmospheric bands and the Great Red Spot extend much deeper than previously thought, and has provided data suggesting a diffuse rather than compact core. The analysis of the gravitational field has also allowed determining that the winds observed on the surface extend to depths of about 3,000 kilometers or 1,865 miles, involving about 1% of the planet's total mass. Initially scheduled to conclude in 2018, the Juno mission was extended until 2021 and then further until 2025, allowing more complete coverage of the planet and more detailed observations of the Galilean moons. The probe, at the end of its mission, will be deliberately made to plunge into Jupiter's atmosphere, like Galileo before it, to avoid biological contamination of Europa and other potentially habitable moons. Jupiter's moon system is a veritable miniature solar system with at least 79 confirmed satellites of various sizes. These satellites can be divided into different categories. The 4 large Galilean moons, Io, Europa, Ganymede, and Callisto, an inner group of 4 small moons, Metis, Adrastea, Amalthea, and Thebe, that orbit inside Io's orbit, and numerous groups of irregular moons, probably asteroids captured by the planet's gravity at different times, which orbit at great distances with often eccentric and retrograde orbits. Most of these moons, interestingly, take their names from the lovers of Roman deities, thus creating a curious mythological connection. The 4 Galilean moons are the largest and most interesting, each with unique characteristics that make them worlds unto themselves, worthy of dedicated exploration. Ganymede, the largest, is also the largest moon in the entire solar system, with a diameter of 5,268 kilometers or 3,273 miles, even larger than Mercury. It's the only known moon to possess its own magnetic field, probably generated by a molten iron core. Its surface is divided into 2 types of terrain: dark, older, and heavily cratered regions, and lighter regions characterized by numerous parallel grooves, probably formed by tectonic processes. Like Europa, Ganymede is believed to hide a subsurface ocean, located at a greater depth and trapped beneath layers of ice. It might have several overlapping layers of ice and water, as well as a possible global ocean between the ice layers. A unique characteristic of Ganymede is the presence of a tenuous oxygen atmosphere, produced when solar radiation and charged particles from Jupiter's magnetosphere strike the icy surface, splitting water molecules. Its low reflectivity suggests that its surface is probably composed of dark, colorless rock. Io, the innermost of the Galilean moons, is the most volcanically active body in the solar system, with over 400 active volcanoes continuously erupting sulfur and sulfur compounds, creating a multicolored surface dominated by yellows, reds, and blacks. This intense volcanic activity is fueled by heat generated by powerful tidal forces. Io orbits in a 1 to 2 to 4 gravitational resonance with Europa and Ganymede that keeps its orbit slightly eccentric, causing a tidal deformation that heats the moon's interior until it melts. The thermal energy generated is estimated at 10 trillion watts, about 25 times greater than all the energy used by humanity. Eruptions on Io can project material up to 500 kilometers or 310 miles above the surface, with volcanic plumes visible even from passing space probes. This material, mainly sulfur compounds and sulfur dioxide, falls back to the surface or escapes Io's gravity, feeding the plasma torus that surrounds the moon's orbit and contributing to Jupiter's magnetosphere. Due to Jupiter's gravitational attraction, Io experiences enormous tides in its solid surface that can reach up to 100 meters or 328 feet in height. These tides, in turn, generate enough heat for volcanic activity, giving Io its characteristic mottled yellow-orange appearance. Europa, the second Galilean moon, is one of the most promising places to search for extraterrestrial life in the solar system. Its icy surface, one of the smoothest in the solar system, presents a complex network of cracks and ridges, suggesting the presence of a liquid ocean underneath. This ocean, which is believed to contain more water than all of Earth's oceans combined, is kept liquid by tidal heat generated by the gravitational interaction with Jupiter and the other Galilean moons. Europa's surface is relatively young, with few craters, indicating active geological processes that continue to renew it. Detailed images also show chaotic regions where the surface ice seems to have broken and refrozen, perhaps due to convective currents in the underlying ocean or pockets of liquid water near the surface. The presence of a liquid ocean, combined with the energy provided by tidal forces and possible essential chemical elements for life transported by comets or produced by chemical reactions, makes Europa a primary target for future astrobiology missions. NASA is currently developing the Europa Clipper mission, scheduled for launch in 2024, which will repeatedly fly over the moon to study the composition of its surface and confirm the presence of the underlying ocean. Part of this liquid erupts from Europa's surface in geysers at the moon's south pole. The prospects of finding life on Europa are particularly intriguing for astrobiologists. Europa's subsurface ocean meets all the fundamental requirements for life as we know it: liquid water, essential chemical elements, and a source of energy. The latter is provided by the tidal forces generated by Jupiter and the other Galilean moons, which keep Europa's interior warm despite its distance from the Sun. Some models suggest that Europa's ocean floor might host hydrothermal vents similar to those on Earth, where complex ecosystems thrive completely independent of sunlight. Moreover, recent observations of water vapor plumes erupting from the surface suggest that it might be possible to sample the underlying ocean without having to drill through the thick icy crust. These characteristics have led many scientists to consider Europa as the most promising candidate for hosting extraterrestrial life in our solar system, surpassing even Mars in terms of biological potential. Callisto, the outermost of the Galilean moons, is the third largest moon in the solar system after Ganymede and Titan, Saturn's satellite. Orbiting at a greater distance from Jupiter than the other Galilean moons, Callisto is not locked in the orbital resonances that cause the intense tidal heating of Io, Europa, and Ganymede. Consequently, it is geologically less active, with an ancient, heavily cratered surface that serves as a record of impacts in the inner solar system. The most notable crater is Valhalla, a concentric ring structure 600 kilometers or 373 miles in diameter. Despite its apparent geological inactivity, Callisto might also have a subsurface ocean, suggested by magnetic field measurements indicating the presence of an electrical conductor under the surface. The duration of a day on Jupiter is determined by how fast it rotates. Being the planet with the fastest rotation in our solar system, Jupiter completes a rotation every 10 hours or so. However, it's important to note that as Jupiter is a gas giant, it doesn't rotate as a solid sphere. Jupiter's equator rotates at a speed of 45,500 kilometers per hour, or 28,273 miles per hour, slightly faster than the polar regions. This causes a slight variation in the length of a day on Jupiter, depending on where you are on the planet. For example, at the equator, a day on Jupiter lasts 9 hours and 50 minutes, while around the polar regions, a day on Jupiter is 9 hours and 56 minutes. A surprising fact concerns Jupiter's role as a cosmic cleaner and planetary shield for the inner solar system. Thanks to its enormous mass and consequent strong gravitational attraction, Jupiter has the power to deflect or capture comets and asteroids that might otherwise head towards the inner planets, including Earth. In 1994, astronomers witnessed a spectacular example of this protective role when comet Shoemaker-Levy 9, already captured by Jupiter's orbit, fragmented into about 20 pieces and impacted the planet between July 16th and 22nd, creating enormous dark scars in the atmosphere visible for months. The impact generated explosions equivalent to millions of megatons of TNT, releasing energies that could have caused a mass extinction on Earth. Computer simulations suggest that without Jupiter's presence, the rate of catastrophic impacts on Earth would be 100 to 1,000 times higher, perhaps making the development of complex life impossible. Some astronomers hypothesize that the presence of a Jupiter in the outer zone of a planetary system might be one of the prerequisites for the development of life on rocky planets in the habitable zone, a true cosmic guardian. We should therefore be grateful to Jupiter for having protected Earth, as it is believed that the planet has played an important role in preventing asteroids from hitting us. As we've seen with the extinction of the dinosaurs, a single asteroid impact of catastrophic proportions could drastically change the course of evolution on Earth. Ultimately, without Jupiter's protective influence, life on Earth might not have developed as we know it today. One of the most fascinating aspects of Jupiter is related to its influence on dwarf planets beyond Neptune and on the overall structure of the solar system. Observations show that many objects in the Kuiper Belt have orbital periods that are integer multiples of Jupiter's, a phenomenon known as orbital resonance. This suggests that Jupiter has played a fundamental role in organizing the entire architecture of the outer solar system, moving planets and debris into specific regions of space during the formation of the system. Some models even suggest that in the first millions of years of the solar system, Jupiter migrated inward to the current orbit of Mars and then back outward in a movement called the Grand Tack, which would have completely reshaped the distribution of material in the protoplanetary disk. This model, known as the Nice model, suggests that initially the giant planets formed much closer to each other than they are today, with Neptune and Uranus in positions more internal than where we currently observe them. The gravitational interactions between these planets and an outer disk of planetesimals caused a gradual outward migration, which at some point became unstable. During this instability phase, which is estimated to have occurred about 700 million years after the formation of the solar system, potentially linking to the period of late heavy bombardment observed in lunar rocks, Jupiter would have moved slightly inward, while Saturn, Uranus, and Neptune would have moved outward, with the latter two possibly even exchanging their positions. The question we all ask at this point is, could there be life on Jupiter? Since Jupiter's atmosphere becomes warmer with depth, reaching a temperature similar to ambient temperature at an altitude where the atmospheric pressure is about 10 times greater than on Earth, scientists hypothesize that if life existed on Jupiter, it would be found at this level and would necessarily be airborne. However, these are just theories, as to date no form of life has been discovered on Jupiter. Although Jupiter itself might not be able to support life as we know it, some of its moons have oceans under their crust that could potentially host forms of life. Europa in particular, with its vast subsurface ocean kept liquid by tidal heat, is considered one of the most promising places in the solar system to search for life beyond Earth. This has led to the design of NASA's Europa Clipper mission, which will explore this moon to determine if it could host conditions suitable for life. If we look even further beyond the boundaries of our system, recent discoveries of exoplanets show us that planets similar to Jupiter are relatively common around other stars. However, many of these extrasolar Jupiters have orbital characteristics very different from ours. The so-called hot Jupiters orbit extremely close to their stars, completing an orbit in just a few Earth days. This contrasts sharply with the relatively distant position of our Jupiter, suggesting that planetary migration might be a common phenomena, but with highly variable outcomes. The particular configuration of our solar system, with the giant gas planets in the outer regions and the small rocky worlds in the inner ones, might be one of the elements that made the development of life on Earth possible. A fascinating curiosity is that if Jupiter had grown even more during the formation of the solar system, it could have become a star. In reality, it would have needed to accumulate about 75 to 80 times more mass than its current mass to trigger hydrogen fusion and become a star like the Sun. However, Jupiter already shows some primitive stellar characteristics. It emits more energy than it receives from the Sun, due to slow gravitational contraction and primordial heat trapped inside. This extra energy, about 67% more than that received from the Sun, is radiated mainly in the infrared. If observed in this wavelength, Jupiter glows faintly with its own light. Some scientists classify Jupiter as a sub-brown dwarf, a body halfway between a planet and a true brown dwarf star. In double or multiple stellar systems, objects similar to Jupiter but slightly more massive are common, orbiting around larger stars just as our gas giant orbits around the Sun. Ultimately, Jupiter continues to amaze and fascinate both professional astronomers and enthusiasts. With its storms that last for centuries, its complex system of moons that are worlds unto themselves, and its crucial role in the evolution of the solar system, the gas giant represents a natural laboratory for understanding the physical processes that dominate objects of this class. As we continue our journey through the solar system, Keep in mind that every planet we encounter is not an isolated entity, but part of a complex system of interactions that extends for billions of years into the past and future. Jupiter, with its majestic presence, reminds us that even in the apparently static void of interplanetary space, dynamic and powerful forces are constantly at work, slowly but inexorably sculpting the destiny of our corner of the universe. In the next episode, we'll push even further from the Sun to explore the Lord of the Rings, Saturn, another giant with secrets all its own to reveal. History of Saturn, the solar system's greatest show. We continue our documentary dedicated to the planets of the solar system with the goal of comprehensively describing their history and characteristics. After traversing the scorching plains of Venus, the red deserts of Mars, the torrid world of Mercury, and the colossal storms of Jupiter, it's time to meet the most spectacular of all planets, Saturn, the magnificent Lord of the Rings, so elegant that it has captured humanity's imagination since the first telescopic observation. In this new chapter, we won't simply describe the hypnotic beauty of its ring system, but we'll go beyond, exploring its complex internal structure, its winds that blow at supersonic speeds, the mysterious polar hexagon, and the fascinating family of over 80 moons that accompany it, some of which hide underground oceans and unique geological phenomena. Comprehensive means exactly this: a detailed narrative rich with information and insights that will lead you to look at Saturn with new eyes, appreciating not only its exterior beauty, but also the hidden scientific complexity. Saturn is a planet of surprising elegance, the sixth world from the Sun, so light that it would float on water if there existed an ocean large enough to contain it, so majestic that it's visible to the naked eye from Earth as a golden star, so rapid in its rotation that it completes a turn on itself in just over 10 hours, yet so slow in its orbit that it takes almost 30 Earth years to complete one trip around the Sun. Its rings, extending for hundreds of thousands of miles but only a few yards thick, create an unparalleled cosmic spectacle, while its atmosphere conceals hexagonal storms that defy the laws of physics as we know them. But let's go in order and get to know this planet better through its numbers. With an equatorial diameter of 74,898 miles or 120,536 kilometers, about 9.4 times that of Earth, Saturn is the second largest planet in the solar system. Its mass equals about 95 times that of Earth, but despite its imposing dimensions, its density is surprisingly low, only 0.687 grams per cubic centimeter or 42.9 pounds per square foot, less than the density of water because it's composed mainly of hydrogen and helium. Saturn orbits the Sun at an average distance of 886 million miles or 1.43 billion kilometers, which is 9.5 astronomical units, completing one revolution in 29.46 Earth years. Its orbit is moderately eccentric, with a value of 0.056 that makes its distance from the Sun vary by about 96 million miles or 155 million kilometers between aphelion and perihelion. The gas giant rotates on its axis in 10 hours and 33 minutes at the equator, though like Jupiter, the rotation varies slightly with latitude. This rapid rotation causes polar flattening even more pronounced than Jupiter's, with the polar diameter being almost 7,460 miles or 12,000 kilometers smaller than the equatorial diameter, giving the planet a distinctly oblate shape. The axial inclination is 26.7 degrees, similar to Earth's, which means Saturn experiences pronounced seasons, each lasting about 7 Earth years. The temperature in the upper cloud layers is about minus 288 degrees Fahrenheit or minus 178 degrees Celsius, while pressure and heat increase dramatically as you descend deeper. The surface gravity, measured at the visible cloud level, is slightly less than Earth's, 0.916 times. So, if you weigh 154 pounds on Earth, you'd weigh about 141 pounds on Saturn. These numbers alone, however, cannot tell the true story of this gas giant. Its biography is written in the complex patterns of its cloud bands, its vortices that last for decades, and in that magnificent ring system that has made it the most recognizable planet in the solar system. Devoid of a rocky surface and with an atmosphere that gradually fades toward a possible rocky core, Saturn represents a completely different type of world from the inner rocky planets. Its clouds, organized in bands and zones of different colors that encircle the planet parallel to the equator, are the visible result of powerful jet streams flowing in opposite directions at different latitudes, creating turbulent boundaries where vortices and storms form. The history of observations. The detailed study of Saturn has been possible only after the invention of the telescope, although the planet was known since antiquity as one of the wandering planets visible to the naked eye. Galileo Galilei in 1610 was the first to observe it with a telescope, but the limited resolution of his instrument made him see the planet as having ears or lateral appendages, without being able to understand the true nature of those protuberances. It was only in 1659 that Dutch astronomer Christian Huygens, using a more powerful telescope he had built himself, managed to solve the mystery. Huygens understood that those ears were actually a thin and flat ring, everywhere detached and not touching the planet, inclined towards the ecliptic. This discovery was revolutionary and forever changed our perception of Saturn. In 1675, Italian astronomer Giovanni Domenico Cassini made another fundamental discovery. What Huygens had described as a single ring was actually divided into two parts separated by a dark space. This gap, known as the Cassini division, was the first indication that the ring system was much more complex than initially imagined. Since then, Saturn has continued to fascinate astronomers of every era, always revealing new details and mysteries. Atmospheric composition and structure. Saturn's atmospheric composition largely reflects that of the primordial solar nebula, being composed of about 96.3 molecular hydrogen and 3.25% helium, with significant traces of methane, 0.45%, ammonia, hydrogen sulfide, ethane, propane, and water vapor. However, the proportion of helium is notably lower compared to Jupiter, which has about 10% helium, suggesting that the heavier helium is slowly precipitating towards the planet's interior through a process called helium rain that significantly contributes to the planet's internal heat. Saturn's atmosphere presents a complex stratified structure. The troposphere, the lowest layer, extends from the visible cloud surface to about 62 miles or 100 kilometers altitude, where temperature varies from minus 288 degrees Fahrenheit or minus 178 degrees Celsius at the surface to about 169 degrees Fahrenheit or minus 113 degrees Celsius at the upper limit. Above is the stratosphere, extending to 621 miles or 1,000 kilometers altitude, where temperature gradually increases to reach minus 45 degrees Fahrenheit or minus 43 degrees Celsius due to absorption of solar ultraviolet radiation by hydrocarbons. Even higher, we find the thermosphere, where temperatures can reach 788 degrees Fahrenheit or 420 degrees Celsius. Winds on Saturn are among the fastest in the solar system, reaching speeds of over 1,118 miles per hour or 1,800 kilometers per hour in the equatorial zone, about 5 times faster than the most powerful terrestrial hurricanes. These supersonic winds are powered by the planet's internal heat and rapid rotation, creating a system of jet streams that encircle the planet at different latitudes. Saturn's atmospheric bands, though less contrasted than Jupiter's, show a complex zonal structure with at least 12 distinct bands of alternating winds. One of Saturn's most extraordinary features is the North Polar Hexagon, a gigantic storm with a perfectly hexagonal shape, with sides of about 8,575 miles or 13,800 kilometers each, large enough to contain 4 planets like Earth. First discovered by the Voyager probes in the 80s and studied in detail by the Cassini mission, this phenomena has no precedent in the solar system. The hexagon rotates with a period of 10 hours and 39 minutes, slightly different from the planet's internal rotation measured through radio emissions. It's accompanied by a vortex at the center of the North Pole that rotates at speeds up to 336 miles per hour or 540 kilometers per hour, with an eye about 1,243 miles or 2,000 kilometers in diameter. The hexagon maintains its precise geometric shape through a mechanism not yet fully understood. But laboratory experiments with rotating fluids have demonstrated that similar polygonal structures can form when jet streams of different speeds interact in rotating systems. The structure extends vertically for at least 186 miles or 300 kilometers into the atmosphere, and its long-term stability, observed for over 30 years, remains one of the most enigmatic atmospheric phenomena in the solar system. At the South Pole instead, we find a more conventional but equally impressive vortex with a clearly defined eye, about 4,971 miles or 8,000 kilometers in diameter, similar to that of a terrestrial hurricane but much larger. This vortex is surrounded by clouds rotating at speeds up to 342 miles per hour or 550 kilometers per hour and extends vertically for over 47 miles or 75 kilometers into the atmosphere. Unlike the northern hexagon, the southern vortex shows a more chaotic and time-variable structure. Storms on Saturn, though less frequent than Jupiter's, can be spectacular. The Great White Spot is a recurring phenomenon that appears every 29 to 30 Earth years, about one Saturnian year, in the planet's northern hemisphere. These enormous storms can extend for thousands of miles and last for months, temporarily altering the appearance of the entire affected atmospheric band. The last Great White Spot was observed in 2010 by the Cassini mission and extended until it completely encircled the planet. Internal structure. Saturn's internal structure is presumably similar to Jupiter's, but with some significant differences, reflecting its smaller mass and density. At the center lies a core of rocky, icy material with an estimated mass between 15 and 18 times that of Earth, and a radius of about 15,534 miles or 25,000 kilometers, significantly larger than Jupiter's core in proportion to planetary dimensions. This core is composed mainly of rock, water ice, and heavier compounds like silicates and iron, with an estimated density of about 10 to 12 grams per cubic centimeter, or 624 to 748 pounds per square foot, and a temperature that can reach 21,092 degrees Fahrenheit, or 11,700 degrees Celsius, hotter than the sun's surface. Around the core extends a thick mantle of liquid metallic hydrogen, where pressure is so high, over 3 million times Earth's atmospheric pressure, that electrons are stripped from hydrogen atoms, creating a conductive fluid similar to liquid metal. This layer, about 16,155 miles or 26,000 kilometers thick, is rapidly rotating and generates the planet's magnetic field through the dynamo effect. Temperature in this region varies from about 14,432 degrees Fahrenheit, or about 8,000 degrees Celsius, in the deep part, to 5,432 degrees Fahrenheit, or about 3,000 degrees Celsius, in the upper part. Above the metallic hydrogen lies a vast ocean of liquid molecular hydrogen, about 18,641 miles or 30,000 kilometers deep, where pressure gradually decreases and temperature drops to about 3,632 degrees Fahrenheit or 2,000 degrees Celsius in the deep part and 320 degrees Fahrenheit or 160 degrees Celsius in the upper part. In this region, hydrogen maintains its molecular structure but exists in liquid state due to immense pressure. The transition from liquid hydrogen to the gaseous atmosphere we observe is gradual, without a defined surface. Like Jupiter, Saturn emits significantly more energy than it receives from the Sun, about 2.5 times more to be precise. This extra energy comes from three main sources. The first is primordial heat remaining from the planet's formation 4.6 billion years ago. The second is the slow gravitational contraction of the planet, which continues today at a rate of about 0.04 inches or 1 millimeter per year. The third, and perhaps most significant for Saturn, is helium rain. Helium, heavier than hydrogen, slowly separates and precipitates towards the core through liquid hydrogen, releasing gravitational energy in the process. Saturn's magnetic field is about 600 times more powerful than Earth's, though significantly weaker than Jupiter's, about 20 times less intense. A unique characteristic of Saturn's magnetic field is that it's almost perfectly aligned with the planet's rotation axis. The inclination is only 0.06 degrees, the smallest of all planets in the solar system. This nearly perfect configuration has long puzzled scientists, since magnetic field generation models typically predict significant misalignment. The ring system, a cosmic masterpiece. Saturn's ring system is undoubtedly its most famous and spectacular feature, representing one of the most beautiful and complex phenomena in the solar system. These rings, which extend from the planet for a distance of over 248,548 miles, or 400,000 kilometers, more than the Earth-Moon distance, but have an average thickness of only 33 to 328 feet, or 10 to 100 meters, are composed mainly of 95 to 99% pure water ice particles, with traces of rocky material and organic compounds. The main system is subdivided into several principal rings, designated with alphabet letters in the order of their historical discovery. From the planet outward, we find the D ring, the innermost and most tenuous, followed by rings C, B, and A, the most visible and massive. Then the F ring, thin and dynamically complex. The G ring, extremely weak, and the E ring, the outermost and most extended, fed by Enceladus's geysers. The D ring is the innermost and most tenuous of the main system, extending from about 41,633 miles or 67,000 kilometers to 46,293 miles or 74,500 kilometers from Saturn's center. Composed of extremely fine dust particles, this ring is so thin it was only discovered by the Voyager probes in 1980. Particles in this ring are slowly spiraling towards Saturn due to atmospheric friction and electromagnetic effects. The C ring, also known as the crepe ring due to its transparency, extends from 46,293 miles or 74,500 kilometers to 57,166 miles or 92,000 kilometers from the planet's center. With an average thickness of only 16 feet or 5 meters, it contains several notable structures, including the Colombo division and Maxwell division. A peculiar feature of the C ring are the spokes, radial dark structures that appear and disappear on hourly timescales, probably composed of electrically charged dust particles lifted from the ring's surface by the planet's magnetic field. The B ring is the most massive and opaque of the entire system, containing about 95% of the total ring mass. It extends from 57,166 miles or 92,000 kilometers to 73,015 miles or 117,500 kilometers from Saturn's center, and has a thickness varying from 16 to 49 feet or 5 to 15 meters. Its optical density is so high that it's completely opaque to visible light. The B ring represents an extremely complex structure with thousands of concentric ringlets, density waves, and temporary structures created by gravitational resonances with Saturn's moons. The Cassini division, 2,983 miles or 4,800 kilometers wide, separates the B ring from the A ring and is the most prominent feature visible even from terrestrial telescopes. Contrary to popular belief, it's not completely empty but contains several thin ringlets and diffuse material. The division is maintained primarily by a 2-to-1 resonance with the moon Mimas, which removes particles from this region through accumulated gravitational perturbations over time. The A ring extends from 75,916 miles, or 122,200 kilometers, to 85,016 miles, or 136,800 kilometers, from Saturn's center. One of its most notable features is the Encke division, 202 miles or 325 kilometers wide, within which orbits the small moon Pan, 22 miles or 35 kilometers in diameter, 83,265 miles or 134,000 kilometers from Saturn. Pan acts as a shepherd moon, creating the division through its gravitational attraction and keeping the division's edges clean of debris. The F ring deserves special mention for its dynamic and complex nature. Located 87,122 miles or 140,180 kilometers from Saturn's center, this thin and relatively dense ring is shepherded by two small moons, Prometheus, 53 miles or 86 kilometers in diameter, 86,590 miles or 139,350 kilometers from Saturn, and Pandora, 50 miles or 81 kilometers in diameter, 88,049 miles or 141,700 kilometers from Saturn, which orbit respectively inside and outside the ring. Gravitational interactions with these moons create a dynamic environment where the ring continuously forms knots, braids, and temporary structures that change within hours or days. The E-ring is the outermost and most extended of the Saturnian system, extending from about 111,847 miles or 180,000 kilometers to over 298,261 miles or 480,000 kilometers from the planet's center. It's also the thickest, with heights reaching 1,553 miles or 2,500 kilometers above and below the equatorial plane. The E-ring is continuously fed by the famous geysers of the moon Enceladus, 314 miles or 504 kilometers, 147,909 miles or 238,000 kilometers from Saturn, which eject water vapor and ice particles at sufficient velocities to escape the moon's gravity. Ring particles vary enormously in size, from microscopic dust grains to house-sized boulders. The size distribution approximately follows a power law, with smaller particles much more numerous than larger ones. These particles orbit Saturn following Kepler's laws, with those closer to the planet moving faster than those farther away, creating density waves and complex structures. One of the most surprising discoveries of the Cassini mission was the presence of temporary and dynamic structures in the rings. The spokes are electrostatic phenomena that seem to rotate together with the planet's magnetic field, rather than following normal Keplerian orbital laws. These spokes are more visible when Saturn is in certain positions relative to the Sun and show seasonal variations. Space exploration of Saturn. Saturn's close-up exploration has been a complex undertaking, given the enormous distance from Earth and the hostile environment surrounding the planet. The first probe to visit the gas giant was Pioneer 11 in September of 1979, which provided the first close-up images and confirmed the existence of the magnetic field. It was followed by Voyager 1 in November of 1980 and Voyager 2 in August of 1981, which revolutionized our understanding of the Saturnian system by providing detailed images of the rings and discovering many of the minor moons. The Voyager probes revealed the structural complexity of the rings, discovered the first spokes, identified several new moons, and provided the first detailed measurements of Saturn's atmosphere and magnetic field. However, the real qualitative leap in Saturn's exploration came with the Cassini-Huygens mission, an ambitious collaboration between NASA, the ESA, the European Space Agency, and ASI, the Italian Space Agency. Launched in October of 1997, the Cassini-Huygens mission reached Saturn on July 1, 2004, after a journey of almost 7 years that included gravitational flybys of Venus twice, Earth, and Jupiter to accelerate towards the final destination. The Cassini probe became the first spacecraft to orbit Saturn, while the Huygens probe developed by ESA was destined to land on Titan's surface. On December 5, 2004, Huygens separated from Cassini and began its journey to Titan. On January 14, 2005, the probe entered the Moon's atmosphere and, after a descent of 2 hours and 28 minutes through the dense atmosphere, landed on the surface, becoming the first human-made object to land on a moon in the outer solar system. During its descent and in the following hours, Huygens transmitted extraordinary images and scientific data that revealed a world surprisingly similar to primordial Earth, with rivers, lakes, and plains shaped by liquid methane erosion. The mothership, Cassini, spent 13 years orbiting Saturn, completing 294 orbits and conducting in-depth studies of the planet, its rings, and its moons. The mission, initially planned to last 4 years, was extended multiple times thanks to the probe's excellent health and the extraordinary quality of scientific data collected. Cassini revolutionized our understanding of the Saturnian system, discovering geysers on Enceladus, hydrocarbon lakes on Titan, new moons, and complex ring structures. The mission's final months were dedicated to the grand finale orbits, 22 spectacular orbits that brought Cassini between the planet and its rings into a region never explored before. These final orbits provided unprecedented measurements of Saturn's upper atmosphere composition, internal ring structure, and the planet's gravitational field. The mission deliberately concluded on September 15, 2017, when Cassini was made to crash into Saturn's atmosphere to avoid possible contamination of potentially habitable moons in case of probe control loss. Saturn's moons, a miniature solar system. Saturn has 274 confirmed moons in its orbit, far more than any other planet in our solar system. In March of 2025, astronomers confirmed the discovery of 128 small moons around Saturn, adding to the already large moon count. These moons can be subdivided into different categories: large, regular moons that orbit in the planet's equatorial plane, small inner moons associated with the rings, and numerous groups of irregular moons that orbit at great distances with often eccentric and retrograde orbits. Titan, 3,200 miles or 5,149 kilometers in diameter, 729,235 miles or 1.2 million kilometers from Saturn. Saturn's largest moon and the second largest in the solar system, after Jupiter's Ganymede, is a fascinating world representing one of the celestial bodies most similar to primordial Earth. Larger than Mercury, it possesses a dense atmosphere composed of 98.4% nitrogen and 1.6% methane, with traces of ethane, propane, acetylene, and other complex hydrocarbons. Surface atmospheric pressure is 1.45 times Earth's, making Titan the only satellite in the solar system with a substantial atmosphere. Titan's surface hosts a complete hydrological cycle similar to Earth's, but with liquid methane and ethane instead of water. Data from the Cassini-Huygens missions revealed rivers, lakes, and seas of liquid hydrocarbons, mainly concentrated in polar regions. The largest of these liquid bodies is Kraken Mare in the northern hemisphere, covering an area of about 154,441 square miles or 400,000 square kilometers, and potentially over 984 feet or 300 meters deep. Titan's climate presents pronounced seasons due to Saturn's inclination, with each season lasting about 7 Earth years. Beneath Titan's frozen crust, theoretical models suggest the presence of a subsurface ocean of liquid water, located 31 to 62 miles or 50 to 100 kilometers deep. This ocean could be up to 124 miles or 200 kilometers deep and contain more water than all Earth's oceans combined. The presence of dissolved ammonia could lower water's freezing point, keeping the ocean liquid despite low temperatures. Titan's complex organic chemistry makes it one of the most interesting places for astrobiology. Enceladus, 314 miles or 504 kilometers in diameter, 147,909 miles or 238,000 kilometers from Saturn. A small icy moon has become one of the most intriguing destinations for life research after Cassini discovered spectacular geysers of water vapor and ice particles erupting from its south polar region. These geysers, nicknamed tiger stripes because of the 4 parallel fractures from which they emanate, eject material at speeds up to 497 miles per hour or 800 kilometers per hour, reaching heights over 311 miles or 500 kilometers above the surface. Enceladus's geological activity is powered by tidal heating caused by orbital resonance with Dion and orbital eccentricity maintained by gravitational perturbations from other moons. Beneath Enceladus's icy crust hides a global ocean of salty liquid water about 6 miles or 10 kilometers deep. This ocean is in direct contact with the Moon's rocky core, allowing chemical reactions that could produce molecular hydrogen and other compounds essential for life. Chemical analysis of the geysers revealed the presence of sodium chloride, carbonates, nanometric silica, and molecular hydrogen. Mimas, 246 miles or 396 kilometers in diameter, 115,280 miles or 185,520 kilometers from Saturn, is famous for its giant Herschel crater, which gives it an appearance similar to the Death Star from Star Wars. This monumental crater has a diameter of 81 miles or 130 kilometers and is 6 miles or 10 kilometers deep, with walls rising up to 3 miles or 5 kilometers above the bottom. The impact that created Herschel almost destroyed Mimas. A slightly more powerful collision would have completely fragmented the Moon. Despite its small size, Mimas has a disproportionate gravitational influence on Saturn's ring system, being responsible for creating and maintaining the Cassini division through 2-to-1 orbital resonance. Iapetus, 913 miles or 1,469 kilometers in diameter, 2,212,889 miles or 3.56 million kilometers from Saturn, presents one of the most mysterious features in the Saturnian system: extreme two-tone coloration, with one hemisphere dark as coal, called Cassini Regio, and the other white as fresh snow. This dichotomy is so pronounced it's visible even from terrestrial telescopes. The dark material is probably composed of organic compounds derived from Saturn's outer irregular moons. Another unique feature of Iapetus is the equatorial ridge, a mountain chain up to 12 miles or 20 kilometers high that gives it a walnut-like appearance. Other major moons include Tethys, 662 miles or 1,066 kilometers in diameter, 183,095 miles or 294,670 kilometers from Saturn, characterized by the enormous Osidius crater and the imposing Ithaca chasma. Dione, 697 miles or 1,123 kilometers in diameter, 234,505 miles or 377,400 kilometers from Saturn, with its icy cliffs and bright streaks. And Rhea, 949 miles or 1,527 kilometers in diameter, 327,488 miles or 527,040 kilometers from Saturn, the second largest moon after Titan, with an ancient, heavily cratered surface. Numerous small moons act as ring shepherds. Pan, 22 miles or 35 kilometers in diameter, 83,265 miles or 134,000 kilometers from Saturn, orbits in the Enki division. Daphnis, 5 miles or 8 kilometers in diameter, 85,405 miles or 137,500 kilometers from Saturn, in the Keeler division, while Prometheus and Pandora maintain the complex structure of the F-ring. Future exploration prospects. Currently, there are no specific missions to Saturn in advanced development stages, but several ambitious concepts are under study. NASA's Dragonfly mission, approved for launch in 2027 with arrival at Titan in 2034, represents the next big step in Saturnian system exploration. This drone, powered by a radioisotope thermoelectric generator, will be able to fly in Titan's dense atmosphere for over 2 years, exploring various sites of astrobiological and geological interest. Future mission concepts include dedicated Enceladus orbiters that could fly through the geysers to directly sample the subsurface ocean, potentially detecting signs of microbial life. These missions would require advanced in situ biochemical analysis technologies and efficient propulsion systems for multiple orbital maneuvers in the Saturnian system. Sample return missions from Enceladus or Titan are considered the holy grail of Saturnian system exploration, but would require significant advances in space propulsion and sample preservation technologies for the long return journey. Telescopic observation continues to provide new information, especially through the James Webb Space Telescope, which can study Saturn's and its moon's atmospheres in infrared with unprecedented resolution. Conclusion: the eternal jewel. Saturn continues to represent one of the most fascinating natural laboratories in the solar system and a timeless symbol of cosmic beauty. With its majestic rings dancing in complex configurations, its moons hiding oceans and showing exotic geologies, and its atmosphere concealing storms with impossible geometries, the sixth planet from the Sun remains a monument to the extraordinary diversity and complexity of the universe. The discoveries of the Cassini mission have transformed our understanding of this world, revealing a dynamic and interconnected system where unique physical and chemical processes create phenomena that challenge our understanding and expand our scientific horizons. From hexagonal storms to icy geysers, from seasonal cycles lasting years to rings that continuously renew themselves, Saturn reminds us that the universe is full of wonders waiting to be discovered. As we look toward the future of space exploration, Saturn and its moons remain priority destinations for understanding not only the formation and evolution of our solar system, but also the possibilities of life beyond Earth. Its icy moons could host microbial ecosystems that would redefine our understanding of life in the universe, while its rings continue to serve as a natural laboratory for studying the processes governing planetary formation. In this golden giant floating in cosmic darkness, surrounded by its retinue of moons and glittering rings, we find not only an object of scientific study, but a reminder of the extraordinary beauty and complexity of the universe we call home. Saturn teaches us that even in the most remote and apparently inhospitable regions of the cosmos, nature can create structures of beauty and precision that surpasses any human artwork. History of Uranus, the coldest and strangest planet in the solar system. We continue our journey through the solar system. After exploring Saturn's hexagonal storms and its hidden oceans, it's time to venture even farther out, toward the icy regions, to encounter one of the most enigmatic and bizarre worlds, Uranus, the ice giant that defies every planetary convention. This planet isn't just a world of extreme climates and exotic compositions, but represents a true cosmic anomaly that continues to surprise astronomers. A giant that rotates completely on its side, like a ball rolling along its orbit, alternately showing its poles to the sun for entire decades. A world where seasons last more than 20 Earth years, and where the atmosphere reaches temperatures so extreme that it becomes the coldest place in the solar system, even more frigid than Neptune, despite being much closer to the sun. What do you say? Shall we pay it a little visit? Uranus is a planet that defies every expectation. The seventh world from the sun, so distant that sunlight takes almost 3 hours to reach it. So cold that methane crystallizes in its upper atmosphere. So strange in its rotation that astronomers have had to redefine the concepts of North Pole and South Pole to describe it. With its characteristic blue-green coloration and its incredible axial tilt of 82 degrees, Uranus literally appears lying on its side as it orbits the sun, creating a seasonal system unique in the solar system. But what makes this icy giant so special? With a diameter of 31,763 miles or 51,118 kilometers, about 4 times that of Earth, Uranus is the third largest planet in the solar system, but fourth by mass, since its density of 1.27 grams per cubic centimeter or 79.3 pounds per cubic foot is significantly lower than that of Neptune, 1.64 grams per cubic centimeter or 102.4 pounds per square foot. It orbits at an average distance of 1.78 billion miles or 2.87 billion kilometers or 19.2 astronomical units from the Sun, completing one revolution in 84 Earth years, essentially the duration of an entire human lifetime. The ice giant rotates on its axis in 17 hours and 14 minutes, but here begins its strangeness. The rotation axis is tilted 82.2 degrees relative to the orbital plane, which means Uranus rotates practically on its side. This unique characteristic means that during the long Uranian year, each pole receives continuous sunlight for 42 Earth years, followed by 42 years of complete darkness. Surface gravity is slightly less than Earth's, 0.886 times. So a person weighing 154 pounds on Earth would weigh about 136 pounds on Uranus. The average temperature in the upper atmosphere is minus 371 degrees Fahrenheit or minus 224 degrees Celsius, making it paradoxically colder than Neptune, despite being closer to the Sun. This thermal enigma is due to the fact that Uranus emits much less internal heat compared to other gas giants, for reasons still not completely understood by planetary science. A new planet after millennia. The story of Uranus's discovery is as fascinating as the planet itself. Until March 13, 1781, humanity knew only 6 planets in the solar system, from Mercury to Saturn. That night, in the spa town of Bath, England, a German musician, naturalized as British, named William Herschel was conducting a methodical observation of the sky with a reflecting telescope of his own construction, equipped with a 6-inch or 15-centimeter diameter mirror. Herschel wasn't a professional astronomer, but an enthusiast who had developed extraordinary skill in telescope construction. Together with his sister Caroline, who would become the first paid woman astronomer in history, William spent nights observing double stars in an attempt to measure stellar parallaxes. That particular evening, while scanning the constellation Gemini, he noticed an unusual object that appeared slightly larger than surrounding stars and showed a clearly visible disk. Initially, Herschel thought he had discovered a comet. The object moved slowly against the stellar background, a characteristic that clearly distinguished it from fixed stars. But in the following weeks, when other astronomers calculated its orbit, it became evident that this was something much more significant: a new planet, the first to be discovered in modern times, and the first identified thanks to a telescope. Herschel's discovery not only doubled the known size of the solar system, but also demonstrated that worlds existed beyond the imagination of the ancients. As a reward for his discovery, King George III appointed Herschel court astronomer and granted him a pension that allowed him to dedicate himself completely to astronomy. Herschel initially proposed calling the new planet Georgium Sidus, or George's star, in honor of the sovereign, but eventually the name Uranus prevailed, suggested by German astronomer Johann Bode, maintaining the tradition of naming planets after figures from classical mythology. Composition and structure: a different giant. Uranus belongs to the category of ice giants, a distinction that separates it both from gas giants like Jupiter and Saturn and from the inner rocky planets. Its composition is dominated by materials that astronomers call ices, not in the sense of frozen water, but volatile substances like water, methane, and ammonia in supercritical phase, along with hydrogen and helium. Uranus's internal structure is organized into 3 main layers. At the center lies a small rocky core composed of silicates and iron-nickel, with a mass of about 0.55 Earth masses and a radius representing less than 20% of the planetary radius. This core is surrounded by a massive mantle of hot ices, mainly water, methane, and ammonia in fluid form, which constitutes most of the planet's mass, about 13.4 Earth masses. Everything is wrapped in a relatively thin atmosphere of hydrogen and helium that represents only about 0.5 Earth masses. What makes Uranus truly unique is its magnetic strangeness. The planet's magnetic field isn't aligned with the rotation axis as would be expected, but is tilted a full 58.6 degrees relative to it. Moreover, the center of the magnetic field is offset by about 1/3 of the planetary radius from the planet's geometric center. This bizarre configuration suggests that the magnetic field might be generated not in the deep core, but in the intermediate layers of the conductive ice mantle. Uranus's atmosphere is composed of 83% molecular hydrogen, 15% helium, and 2% methane, with traces of water vapor and ammonia. It's precisely the methane that gives the planet its characteristic blue-green coloration. This gas strongly absorbs red light while reflecting blue and green wavelengths. The presence of methane in the upper atmosphere was unexpected, given that at those temperatures, minus 371 degrees Fahrenheit or minus 224 degrees Celsius, it should be completely frozen. An extreme and mysterious climate. Uranus's climate is governed by its extraordinary axial tilt, which creates a seasonal system unique in the solar system. Unlike other planets where seasons are caused by varying distance from the Sun, on Uranus they depend entirely on which pole is facing our star. During Uranian summer, one pole receives direct and continuous sunlight for 42 Earth years, while the other remains in complete darkness. Then, the situation reverses for another 42 years. Despite this extreme configuration, Uranus shows surprisingly fast winds that can reach 560 miles per hour or 900 kilometers per hour, among the fastest in the solar system. These winds blow mainly in the direction of the planet's rotation, but the mechanism that powers them remains mysterious, given that Uranus receives so little solar energy and generates very little internal heat. The Voyager 2 probe, which visited Uranus in 1986, observed an apparently calm atmosphere with very few visible features. However, more recent observations from the Hubble telescope have revealed that Uranus can develop dynamic storm systems, especially when approaching equinoxes, moments when both hemispheres receive solar illumination. A particular mystery concerns Uranus's atmospheric temperature. Despite being closer to the Sun than Neptune, Uranus is systematically colder. While Neptune emits 2.6 times more energy than it receives from the Sun, Uranus emits almost the same amount it receives, suggesting a much less thermally active interior. Theories range from different internal composition to consequences of the impact that might have caused its anomalous rotation. Hey guys, just a moment before we continue. Be sure to join the Insane Curiosity channel. Click on the bell. You'll help us to make products of even higher quality. A complex system of rings and moons. Uranus possesses a ring system discovered only in 1977, when astronomers aboard the Kuiper Airborne Observatory observed the planet occulting a distant star. To their surprise, the stellar light dimmed several times before and after the main occultation, revealing the presence of thin, dark rings. Uranus's ring system is composed of 13 confirmed rings, very different from Saturn's spectacular ones. Uranus's rings are extremely dark, reflecting only 2% of incident light, and are probably composed of organic material altered by radiation. The most prominent is the Epsilon ring, about 62 miles or 100 kilometers wide, with particles ranging from fine dust to boulders several yards across. Uranus's 28 known moons are equally unique in the solar system. Unlike moons of other planets, which take names from Greek or Roman mythology, those of Uranus are named after characters from the works of William Shakespeare and Alexander Pope, earning them the nickname literary moons. This tradition began with John Herschel, son of Uranus's discoverer, who in 1852 named the first 4 known moons. Besides the 5 major moons, Uranus possesses 23 minor moons discovered mainly by the Hubble telescope and advanced ground-based observations. 10 of these were identified by Voyager 2 in 1986. Cordelia, 25 miles or 40 kilometers in diameter, Ophelia, 27 miles or 43 kilometers, Bianca, 32 miles, 51 kilometers, Chrysidia, 50 miles or 80 kilometers, Desdemona, 40 miles or 64 kilometers, Juliet, 58 miles, 94 kilometers, Portia, 84 miles or 135 kilometers, Rosalind, 45 miles or 72 kilometers, Belinda, 56 miles or 90 kilometers, and Puck, 101 miles or 162 kilometers. These small moons orbit between the rings and major moons, some acting as shepherds to maintain ring structure. The outer irregular moons discovered between 1997 and 2003 include Caliban, Sycorax, Prospero, Setebos, Stefano, Trinculo, Francisco, Margaret, and Ferdinand. These moons, with diameters between 5 and 93 miles or 8 and 150 kilometers, orbit at enormous distances, 2.5 to 12.4 million miles or 4 to 20 million kilometers, on retrograde and highly eccentric trajectories, suggesting they are asteroids captured by Uranus's gravity. The most recent discovery dates to November 2023, bringing the total to 28 confirmed moons. Miranda, 294 miles or 472 kilometers in diameter, 80,654 miles or 129,800 kilometers from Uranus, the smallest of the major moons, is perhaps the most fascinating and mysterious. Its surface presents a patchwork appearance with terrains of different ages juxtaposed in apparent random ways, a unique characteristic in the solar system. Canyons 12 miles or 20 kilometers deep, 12 times deeper than the Grand Canyon, carved through its icy surface, while oval structures called coronae indicate complex geological processes. Its density of 1.2 grams per cubic centimeter or 74.9 pounds per cubic foot suggests an ice-rich composition. Some theories propose that Miranda was fragmented by catastrophic impacts and then reassembled under its own gravity, explaining its fragmentary appearance. Ariel, 719 miles or 1,158 kilometers in diameter, 118,000 miles or 191,200 kilometers from Uranus, is the brightest of the Uranian moons, with an albedo of 23%. Its relatively young surface shows few large craters, but many small ones, indicating recent geological renewal events. Intersecting valleys and scarps across the surface, some partially filled with material that may have upwelled from the interior. Its density of 1.67 grams per cubic centimeter or 104.2 pounds per cubic foot indicates a mixed composition of ice and rock in nearly equal proportions. Umbriel, 726 miles or 1,169 kilometers in diameter, 165,300 miles or 266,000 kilometers from Uranus, is the darkest of the major moons, reflecting only 16% of incident light, blacker than asphalt. Its ancient surface is densely cratered, similar to lunar highlands. A mysterious bright ring, 87 miles or 140 kilometers in diameter, stands out on its dark surface, whose origin remains unexplained. Its density of 1.4 grams per cubic centimeter or 87.4 pounds per cubic foot suggests a balanced composition of ice and rock. Titania, 981 miles or 1,578 kilometers in diameter, 271,100 miles or 436,300 kilometers from Uranus, the largest moon in the system, presents varied terrain with craters, canyons, and smooth plains. Valleys up to 62 miles or 100 kilometers deep carve the surface, testifying to past tectonic activity. Its density of 1.71 grams per cubic centimeter or 106.8 pounds per cubic foot is the highest among Uranian moons, indicating greater rocky content. Recent models suggest Titania might harbor a residual ocean up to 31 miles or 50 kilometers deep beneath its icy crust. Oberon, 946 miles or 1,523 kilometers in diameter, 362,600 miles or 583,500 kilometers from Uranus, the outermost of the major moons, shows an ancient densely cratered surface, reminiscent of Saturn's moon Rhea. Several craters display bright rays and central material, indicating relatively recent impacts. Its density of 1.63 grams per cubic centimeter or 101.8 pounds per cubic foot is similar to Titania's. Like Titania, it might hide a subsurface ocean maintained by thermal metamorphism processes. Visited by a single probe, Voyager 2. Uranus's close-up exploration has been entrusted exclusively to the Voyager 2 probe, which reached the planet on January 24, 1986, after an 8.5-year journey. This encounter represents one of the triumphs of space engineering. Voyager 2 had to be reprogrammed to adapt to Uranus's anomalous rotation and unusual magnetic fields. During the close flyby, passing just 50,600 miles or 81,500 kilometers from the cloud tops, Voyager 2 transmitted over 7,000 images and an enormous amount of scientific data. The probe discovered 10 new moons, 2 new rings, and provided the first detailed measurements of Uranus's magnetic field. The images revealed an apparently monotonous world with an atmosphere almost devoid of distinctive features, a stark contrast to Jupiter's turbulent storms and Saturn's colored bands. However, Voyager 2's data has continued to reveal secrets for decades. In 2020, a reanalysis of magnetic data identified a gigantic magnetic bubble, plasmoid, that had detached from Uranus during the probe's passage, suggesting much more dynamic magnetospheric processes than initially understood. Voyager 2's scientific legacy has also highlighted how little we still know about Uranus. The probe observed the planet during southern solstice, when one pole was facing almost directly toward the Sun. This means we've never closely observed Uranus's atmosphere during other seasons, leaving many questions about its seasonal atmospheric dynamics. After Galileo at Jupiter, Cassini at Saturn, and Juno continuing to study Jupiter, ice giants remain the last class of solar system planets without a dedicated orbiting explorer. International efforts to realize such a mission are intense and coordinated. The European Space Agency has included ice giant exploration in its Strategic Voyage 2050 program, while NASA has identified a Uranus mission as an absolute priority for the next decade. Advanced mission concepts include combinations of orbiters, atmospheric probes, and even landers on icy moons. Unsolved mysteries and future prospects. Uranus remains one of the least understood planets in the solar system, with more questions than answers. The origin of its anomalous rotation is still debated. A gigantic impact during planetary formation, chaotic orbital migration, or perhaps a combination of catastrophic events. New theories suggest that instead of a single massive impact, a series of smaller collisions with moon-sized objects might have gradually tipped the planet over. Its eccentric magnetic field suggests internal processes fundamentally different from those of other giants. The lack of internal heat. Uranus emits only 1.06 times the energy it receives from the Sun, much less than other gas giants, challenges planetary evolution models. This energy deficit might be considered to the great impact that caused its anomalous rotation, possibly dispersing the planet's primordial heat into space. Even its apparently calm atmosphere might hide complex dynamics that we only partially observe from Earth. Recent observations from the James Webb Telescope have revealed unprecedented details of rings and seasonal storms, suggesting Uranus is much more active than Voyager 2 observed during its brief encounter. The most recent studies suggest that Uranus's major moons might harbor residual oceans beneath their icy surfaces. Titania and Oberon might maintain liquid layers up to 31 miles or 50 kilometers thick thanks to late thermal metamorphism, while Ariel and Umbriel might have thinner oceans less than 19 miles or 30 kilometers. These oceans, if they exist, might be hypersaline and therefore detectable through induced magnetic fields, opening new possibilities for astrobiology. Uranus as archetype of extrasolar worlds. Uranus and Neptune represent much more than simple curiosities in our solar system. They are archetypes of the most common class of planets in the universe. Observations from the Kuiper Space Telescope have revealed that planets with masses and sizes intermediate between Earth and Neptune, the so-called super-Earths and mini-Neptunes, are the most abundant among known exoplanets. These worlds, with radii between 1.8 and 4.0 Earth radii, represent a planetary category completely absent from our solar system but dominant in the galaxy. Most orbit very close to their host stars, completing an orbit in less than 100 days, creating extreme environmental conditions that might be common in the universe. Studying Uranus and Neptune therefore provides us with a natural laboratory for understanding physical processes that might be fundamental to billions of worlds throughout the Milky Way. The unique composition of ice giants, dominated by volatile compounds like water, methane, and ammonia rather than hydrogen and helium, represents a key to understanding how these intermediate worlds form. Current planetary formation models struggle to explain how Uranus and Neptune could have accreted their masses in their present position, where the protoplanetary disk was too rarefied and formation timescales too long. Three main scenarios compete to explain ice giant formation. Core accretion in their current position, unlikely given the low density of the outer disk. Formation closer to the Sun followed by outward migration, supported by the Nice model, and direct gravitational instability of the protoplanetary disk that would create massive protoplanets in relatively short times. The last scenario is particularly intriguing because it could explain rapid ice giant formation even in short-lived protoplanetary disks, which exist for only a few million years. Regions of slightly higher density in the disk could collapse directly into protoplanets with planetary density and timescales of thousands of years, much faster than the 100,000 to 1 million years required by traditional core accretion. To conclude, Uranus reminds us that the universe is full of surprises that challenge our expectations. This giant that rotates on its side with its frigid atmosphere and magnetic mysteries represents a fundamental chapter in solar system history. Its discovery revolutionized our understanding of cosmic vastness, while its unique characteristics continue to challenge our planetary models. In this distant world where seasons last decades and winds blow at supersonic speeds through an atmosphere of frozen methane, we find a reminder of incredible planetary diversity. Uranus teaches us that even in the most remote and apparently inhospitable places in the cosmos, nature can create phenomena of complexity and beauty that surpasses our imagination. Okay, folks, that's all for Uranus. Our journey will continue with Neptune, the last of the major planets, a world of devastating winds and icy moons that will complete our tour of the most remote domains of the solar system. History of Neptune, the last guardian of the solar system. Here we are at the final stop of our extraordinary journey through the most extreme frontiers of the solar system. After exploring Uranus's magnetic anomalies and its upside-down rotation, we're heading toward the ultimate planetary frontier, Neptune, the eighth and most distant of the major planets. A world of titanic storms and profound mysteries that reigns supreme in the frigid cosmic periphery. This ice giant doesn't simply represent the final chapter of our exploration, but embodies the triumph of mathematics over chance. The first planet in history discovered not through direct observation, but through theoretical calculations. A world where winds reach supersonic speeds that defy all physical logic, where a great dark spot appears and disappears like an atmospheric phantom, and where a captured moon dances an orbital dance backwards, challenging gravitational conventions. Are you ready for this final epic journey to the edges of our planetary system? Neptune dominates the most remote regions of the solar system from an average distance of 4.5 billion kilometers, or 2.8 billion miles, or 30.1 astronomical units from the Sun. At this incredible distance, sunlight takes more than 4 hours to reach this frozen world, where illumination is 1,000 times weaker than what we experience on Earth. Yet, as we're about to see, despite this energy poverty, Neptune turns out to be the most dynamic and meteorologically active planet in the entire solar system. With a diameter of 49,528 kilometers or 30,775 miles, Neptune is slightly smaller than Uranus at 50,724 kilometers, but its higher density, 1.64 grams per cubic centimeter versus 1.27, gives it a mass equal to 17.5 times that of Earth compared to Uranus's at 14.5. Neptune's orbital period extends for 164.8 Earth years, a time so long that since its discovery in 1846, it has completed barely one complete revolution around the Sun in 2011. Rotation on its own axis takes 16 hours and 6 minutes, slightly faster than Uranus. Unlike its predecessor, Neptune's rotational axis has a normal inclination of 28.3 degrees, similar to Earth's, creating conventional seasons that last over 40 Earth years each. Despite receiving only 1,000th of the solar energy that reaches Earth, Neptune maintains atmospheric temperatures of minus 218 degrees Celsius or minus 360 degrees Fahrenheit, paradoxically warmer than those of Uranus despite being farther from the Sun. This thermal paradox is explained by the fact that Neptune radiates 2.6 times more energy than it receives from our star, testifying to an interior still active from geological and thermal standpoints. A planet found through celestial mechanics. The story of Neptune's discovery represents one of the most fascinating chapters in modern astronomy, demonstrating the predictive power of mathematics and theoretical physics. It all began with a supposed orbital anomaly. After Uranus's discovery in 1781, astronomers noticed that the planet didn't follow exactly the orbit predicted by Newton's laws. These orbital perturbations suggested the presence of another massive body gravitationally influencing Uranus's movement. In 1843, young English mathematician John Couch Adams, then a student at Cambridge, undertook the ambitious challenge of calculating the unknown planet's position based exclusively on the observed perturbations. His calculations, completed in 1845, identified a specific region of the sky where the mysterious eighth planet should be located. However, the British astronomical establishment showed little interest in Adams' predictions, not following up on his request for direct observations. Meanwhile, in France, astronomer Urbain Le Verrier was conducting independent calculations, arriving at surprisingly similar conclusions. Le Verrier managed to convince German astronomer Johann Galle at the Berlin Observatory to search for the planet in the predicted position. On the evening of September 23, 1846, Galle and his assistant Heinrich d'Arrest pointed their telescope toward the constellation Aquarius and, comparing observations with detailed star maps, identified an object that didn't appear on the charts, located less than 1 degree from the theoretically calculated position. This discovery sparked an international controversy over scientific priority, with the British and French claiming credit. Today, Adams and Le Verrier are recognized as co-discoverers of Neptune, celebrating the triumph of the scientific method and international collaboration. The name Neptune, suggested by Le Verrier himself in honor of the Roman god of the seas, was universally accepted, maintaining the mythological tradition in planetary nomenclature. Anatomy of an ice giant. Neptune's atmosphere, relatively thin compared to the planet's size, is composed of 83% molecular hydrogen, 15% helium, 1% methane, and traces of deuterated hydrogen, ethane, and water vapor. Like Uranus, it's the atmospheric methane that gives Neptune its characteristic deep blue coloration, absorbing red light and reflecting blue wavelengths. However, Neptune's blue appears more intense and vivid than that of Uranus, suggesting the presence of an additional component not yet identified that amplifies the selective light absorption. The atmosphere hosts the most extreme and dynamic meteorological phenomena in the solar system, a paradox considering its distance from the sun and the consequent scarcity of available external energy. Neptune's winds reach speeds that defy conventional physical understanding, up to 2,100 kilometers per hour or 1,300 miles per hour, making them the fastest ever recorded on any planet in the solar system, even exceeding the speed of sound on Neptune. These supersonic winds blow mainly in a retrograde direction, opposite to planetary rotation, a phenomenon that further amplifies the mystery of their origin. The energy source of these winds remains one of the great enigmas of planetary meteorology. While terrestrial winds derive from differential solar energy and Jupiter's are powered by the planet's internal heat, Neptune combines both energy sources uniquely, with internal heat dominating despite the presence of a weak solar gradient. Neptune's most famous atmospheric feature was the Great Dark Spot, an Earth-sized storm system observed by the Voyager 2 probe in 1989. This gigantic anticyclonic storm, similar in structure to Jupiter's Great Red Spot, had peripheral winds of 2,400 kilometers per hour and moved westward at 1,200 kilometers per hour relative to surrounding clouds. However, when the Hubble telescope observed Neptune in 1994, the Great Dark Spot had completely disappeared, replaced by a new storm in the Northern Hemisphere. This behavior highlights the dynamic and transitory nature of Neptunian storms, which form, evolve, and dissipate on much shorter timescales compared to the stable meteorological systems of Jupiter and Saturn. Hubble observations have documented the appearance and disappearance of at least 6 large dark spots over 3 decades, suggesting these systems have typical lifespans of 2 to 6 Earth years. Beyond the great storms, Neptune's atmosphere shows subtle horizontal bands, bright circular clouds that change on hourly timescales, and southern cloud structures that appear linked to seasonal changes. The brightest clouds are composed of methane crystals forming in the upper atmospheric layers, while deeper formations might contain ammonium hydroxide and hydrogen sulfide. This blue giant's magnetic field also presents unique and puzzling characteristics. Like Uranus, it's not aligned with the planetary rotation axis, but is tilted 47 degrees relative to it. The magnetic field center is also offset by 0.55 planetary radii from the planet's geometric center, an even more extreme characteristic than that observed on Uranus. This configuration suggests the magnetic field is generated in intermediate layers of the conductive mantle rather than the deep core, supporting models proposing distributed dynamo mechanisms in these exotic worlds. The internal structure also reveals a complex architecture that clearly distinguishes it from the gas giants of the inner solar system. At the planet's center extends a rocky core composed mainly of silicates, iron, and nickel, with an estimated mass between 0.55 and 1.0 Earth masses, and temperatures that could reach 5,100 degrees Celsius, comparable to the solar surface. This core is surrounded by a massive mantle of hot ices, mainly water, methane, and ammonia in supercritical phase, which constitutes most of the planetary mass. These materials, compressed at enormous pressures and heated by planetary depths, behave like electrically conductive fluids, contributing to the generation of a strong magnetic field. The mantle extends for about 80% of the planetary radius and contains approximately 10 to 15 Earth masses of material. Only Voyager 2 arrived here too. Direct exploration of Neptune, like that of Uranus, remains entrusted exclusively to the Voyager 2 probe, which completed its grand tour of the outer planets with a magnificent flyby of the Neptunian system on August 25, 1989. This encounter represented the culmination of a 12-year mission and marked the final stage of initial exploration of all major planets in the classical solar system. Voyager 2 approached Neptune to within 4,950 kilometers of the cloud tops, the closest distance reached by the probe during all its planetary encounters. During this crucial flyby, the probe transmitted over 9,000 images and collected scientific data that revolutionized our understanding of this remote world. The discovery of the Great Dark Spot, supersonic winds, Triton's geysers, and 6 new moons transformed Neptune from a telescopic point of light into a complex and dynamic world. For the future, several space agencies are developing mission concepts for the ice giants. NASA has identified a mission to the Uranus and Neptune systems as maximum scientific priority for the next decade, while the European Space Agency includes ice giant exploration in its long-term strategic program, Voyage 2050. A unique moon system, the realm of Triton. Neptune's satellite system is distinctly different from those of other giants due to the overwhelming dominance of a single giant moon, Triton. This frozen world, with a diameter of 2,704 kilometers or 1,680 miles, contains over 99.5% of the mass of the entire Neptunian satellite system, an unprecedented mass concentration among the outer planets. Triton orbits Neptune at a distance of 354,800 kilometers in a retrograde direction, completing a revolution in 5.88 Earth days in perfect gravitational synchrony that keeps the same face always turned towards the planet. The retrograde orbit is highly unusual for a moon of such size and strongly suggests that Triton is a captured object, probably a large Kuiper Belt asteroid that was trapped by Neptune's gravity during a close encounter billions of years ago. Triton's surface presents unique characteristics in the solar system, with surface temperatures of minus 235 degrees Celsius or minus 391 degrees Fahrenheit. It's one of the coldest places in the solar system. it shows clear evidence of recent geological activity. Its young surface, with very few impact craters, is dominated by icy plains, rough terrain called cantaloupe terrain for its resemblance to melon rind, and fracture systems indicating active tectonic processes. The most surprising discovery was that of Triton's nitrogen geysers, first observed by Voyager 2. These gas jets reach heights of 8 kilometers above the surface and are carried by winds for over 150 kilometers, depositing dark material in streaks that stain the bright ice. The mechanism powering these geysers remains debated. It could be seasonal heating of nitrogen deposits beneath the surface, or endogenous processes related to tidal heating. Triton's atmosphere, though tenuous, is composed mainly of nitrogen with traces of methane and carbon monoxide. Atmospheric pressure is about 70,000 times weaker than Earth's, but sufficient to support clouds and haze in the ionosphere. This atmosphere is in dynamic equilibrium with surface deposits of frozen nitrogen, which sublimate and recondense following seasonal cycles lasting decades. Neptune's other moons pale in comparison to Triton. Nereid, the second largest moon with a 340-kilometer diameter, follows an extremely eccentric orbit that takes it from 1.4 to 9.6 million kilometers from the planet. This unusual orbit could be the result of gravitational perturbation caused by Triton's capture, which would have disrupted Neptune's original satellite system. The minor inner moons, Naiad, Thalassa, Despina, Galatea, Larissa, and Proteus, are small irregular bodies with diameters between 54 and 420 kilometers that orbit among Neptune's rings. These moons are probably fragments of the original satellite system, destroyed and reformed after Triton's capture. Proteus, the largest of these inner moons, has a distinction of being the largest celestial body that hasn't assumed a spherical shape, remaining notably irregular despite its considerable size. Thin and dynamic rings. Neptune's ring system, discovered in 1984 through stellar occultation observations, comprises 5 main rings named after astronomers involved in the planet's discovery: Gaul, Leverrier, Lassell, Arago, and Adams. These rings are notably different from Saturn's spectacular ones, being extremely dark, thin, and variable in density. The Adams ring, the outermost and most interesting, presents a unique characteristic in the solar system: bright arcs concentrated in specific centers of the ring rather than a uniform distribution of material. These arcs, named Liberté, Égalité, Fraternité, and Courage, maintain their structure thanks to gravitational resonance with the moon Galatea, which confines ring material to specific regions through complex gravitational interactions. Neptune's rings are composed of dark organic particles that reflect only 2 to 3% of incident light, similar in comparison to materials found in C-type asteroids and Kuiper Belt objects. Their age is estimated at hundreds of millions of years, relatively young on geological scales, suggesting they're products of small moon fragmentation caused by meteoritic impacts or orbital instabilities. The variability observed in Neptune's rings, documented by Hubble telescope and Very Large Telescope observations, indicates these systems are dynamic and in continuous evolution. Some ring sectors seem to appear and disappear on yearly timescales, while others show brightness variations that could be linked to seasonal changes in solar illumination. Neptune and the universe of exoplanets. Neptune's importance transcends our solar system's boundaries, extending to the formation of extrasolar planets. Ice giants, as we saw with Uranus, represent the archetypes of a dominant planetary class in the observable universe. Subneptunes, or super-Earths, worlds with intermediate masses between Earth and Neptune that constitute the majority of known exoplanets. Kepler Space Telescope observations have revealed that planets with radii between 1.8 and 4.0 Earth radii are the most common in the galaxy, despite this category being completely absent in our solar system between Earth and Neptune. Many of these exoplanets orbit very close to their parent stars, completing orbits in days or weeks and experiencing extreme environmental conditions that could nonetheless be representative of billions of similar worlds. Neptune's composition and internal structure provide fundamental models for understanding these distant worlds. The transition between planets dominated by rock and metals, like Earth, and those dominated by volatile elements, like Neptune, might occur around 3 to 4 Earth radii, defining a critical frontier in planetary evolution that separates super-Earths from mini-Neptunes. Ice giant formation processes remain debated, with direct implications for understanding exoplanets. If Neptune formed through rocky core accretion followed by volatile capture, this process should be common in other planetary systems too. If instead it formed through direct gravitational instability of the protoplanetary disk, formation times would be much shorter, allowing ice giant formation even in short-duration protoplanetary disks. Neptunian-style exoplanet atmospheres show extraordinary diversity in spectroscopic observations. Some retain dense atmospheres rich in hydrogen and helium, while others seem to have completely lost their primordial gaseous envelope, leaving exposed rocky cores resembling super-Earths. Neptune represents an intermediate case that could help understand atmospheric loss processes and long-term planetary evolution. Final reflections. The last frontier. As we conclude this journey through the solar system's frontiers, from scorching Mercury to Neptune's icy depths, we carry with us the awareness that every world visited has contributed a unique chapter to the great story of planetary evolution. Neptune, the last guardian of our classical solar system, greets us from its cold cosmic distances, and its deep blue shines like a distant beacon, keeper of secrets awaiting future generations of space explorers. All right, guys, keep following us for more extraordinary journeys through the mysteries of the cosmos.